Everyone see my screen?
Yep.
All right, yeah. Thanks for everyone for showing up. This is today's agenda. We'll quickly go through what we've been doing in the last 10 years of Student Challenge, and then we'll go through the details of this year's challenge. And then at the end, repairfact.org, Sam Goldwasser, he'll provide a really short tutorial on homodynamic interferometry. So the vision for the students is it's a great platform, not only to practice your mechatronics skills and team collaboration, but also when you go to the conference, talk with the fellow students from different schools. We forget to do that. I did when I was a student participating in the challenges. And then if you find anyone with gray hair, go talk to them. Most probably they are the world expert in one of the fields of the big precision engineering community. And also the sponsors will be there. If you're hunting for jobs, go chat with them. And it's a great place to demonstrate your hands-on mechatronics skills there. So yeah, this all started in Boston 10 years ago. The first challenge was 3 improv challenges: controls, design, and metrology. Next year, we got a little more ordered, and we hosted this tuning fork penny scanner. Students built a flexure-based stage activated by voice coil to do this. The following year, we made them do a PE logo, write it on the wall using a laser that was mounted on the, again, flexure stages activated by voice coil. In Charlotte in 2017, what you're looking at is one of the student system on a shaker table. We put a laser on the top of the system and pointed to a wall. And this laser point will be shaking quite bad. And once they turn the controller on, the goal was to reduce the motion of the laser, thereby isolating the vibration coming from the shaker table. Next year in Las Vegas, there was a pretty fun conference. We made them measure glass plate thickness down to 100 micrometers. Here's a confocal focus probe the committee built. And here you can see this stage actuated by a voice coil going up and down. And teams also used a capacitance probe to convert the intensity into displacement values. And this is one of the confocal peaks from the measurement. In 2019, in Pittsburgh, we hosted a kibble balance challenge. Coincidentally, this was also the year when the unit kilogram was redefined using Planck's constant, using kibble balance experiments ran in many national metrology institutes in different parts of the world. And 2020, we were going to host a diffraction grating challenge, but as you all know, it's a pandemic year. So as a backup plan, we gave the teams dummy tools. We sent it out to their schools, and they did participate in the challenge virtually. So they built flexure mechanisms, again, using a knife edge sensor as feedback, and they did force control. We sent them a load cell, which they put under the this dummy tool so that they can validate their control of the force. Next year, we got back to hybrid. This was in Minneapolis. This year, we got this really cool XY air bearing stages, which teams used along with the flexure stage that they designed and built to make diffraction gratings using this diamond tool. Last year, students used this really inexpensive but remarkable engineering in a really compact factor, optical pickup units you find in DVD players. And they measured this Alvarez freeform mirror. This has a peak to valley of 50 micrometer height. And the students were able to make measurements with single digit nanometer repeatability in a hotel environment, which was really nice to see. Yeah, here we are this year, interferometric nano positioning challenge. Here you're looking at the X air bearing stage and the interferometer setup that goes with it, and the capacitance probe. The stage also has a built-in line scale with 70 nanometer resolution. None of this is possible without our sponsors, so a big shout out to them. And they don't only provide us monetary support, but also most of the or all of the equipment are provided in loan or as a donation to the committee so that we can organize these challenges in the last 10 years. I'm going to quickly go through the interferometer layout that you will be using this year. So the laser is a linearly polarized laser. When the laser beam is modeled as an electromagnetic wave, when its horizontal and vertical oscillation components are in phase, the beam is called as a linearly polarized beam. Take a look at this new video by 3 Blue, 1 Brown. This really improved my understanding on the whole polarization aspect. So the beam enters a polarized beam splitter in 45-degree angle and splits into two. And if you look at this side, the waves coming out will be oscillating horizontally as it enters a quarter wave plate. This retards, the quarter wave plate should be in 45-degree with respect to this horizontally oscillating beam going through it. As it exits, extraordinary wave and ordinary wave, and one of them get phase shifted by 90 degrees. So this will be circularly polarized. It goes hits the corner cube. As it reflects back, they get phase shifted by another 180 degree. That makes it clockwise circularly polarized. As it exits through the quarter wave plate again, it becomes the p-polarized light, which will be vertically oscillating. So this can pass through the polarized beam splitter. The opposite happens on the other side. We put a 50-50 beam splitter where these two beams get split into 50-50. And you put a circular polarizer in front of it, which is nothing but a quarter wave plate and a linear polarizer attached on top of the other. As these two beams enter through the circular polarizer, they become circularly polarized. The same happens on the other side. As this corner cube moves, these beams shift with respect to each other, causing intensity fringes. If one of the circular polarizer is placed in 45-degree with respect to the other one, the photodiodes observing this intensity will have a 90-degree phase shift to it. So when you plot one versus the other, it'll form a circle. So the displacement of the corner cube is related to the change in phase using this equation, where lambda is the wavelength of the light you will be using, which is the Heaney laser in this case. At the end, as I mentioned earlier, Sam will present his tutorial on homodynamic interferometer. So yeah, now you must have received all the equipment that we sent you. Yeah, go ahead and assemble the interferometer with respect to the pre-assembled stage that came in this big black box. One of the main thing I want to mention is this laser is quite expensive. So unfortunately, if you damage it, we won't be able to provide you another one. So make sure it works fine and let us know. I'm not going to go through in detail of all the assembly. These are pretty self-explanatory. Contact us if you have any questions. So the corner cubes, polarized beam splitter on a tip tilt mount, detector bench with photodiodes and circular polarizers. And this slide shows how to identify the 3 different polarization optics provided. And take a look at this YouTube video as well. You'll be using MEG blocks for mounting. These are like Lego or erector set blocks with M4 threaded inserts and round washers. This is how you'll assemble the optical post and holders from Thor Labs to the breadboard that holds the X stage. The capacitance probe holder, power supplies you'll be using. And these are the, this is the 16-bit DAC amplifier box. You'll read the capacitance probe using a BNC cable. and a aux connector goes to the x-axis air bearing stage. Power supply plugs in here, and this is a interface board which talks to the myrio and the amplifier through this Ethernet cable. Make sure to use the Ethernet cable we sent you because this has a metallic shielding around it, which is necessary to get them to work. And yeah, this is the PCB which reads the photo detector, which plugs to the other side of the myrio. So totally, you have three sensors. One is the interferometer, the second one is the built-in line scale, and the third one is the capacitance probe. They three have their own advantages and a disadvantage, so which I tried to put them together here. So the interferometer has meters of range, nanometer level resolution, but because of the software and the data acquisition limitation, to read it at 3 nanometer resolution, you can only travel at 1/4 millimeters per second. Whereas the capacitance probe, the range is limited, but the resolution and bandwidth is quite large. And with the line scale, the range is 10 millimeter because it's built onto the stage. The resolution is only 70 nanometers, but it can be read quite fast. Yeah, these 3 slides only shows how I came up with these numbers. So yeah, before the preliminary presentation, pretty much 20 days from now, these are just suggested steps. Watch the YouTube videos and use the solid model assembly on GitHub to assemble the interferometer with the stage. Install LabVIEW and use the sample project that's in GitHub. I also go through that in the YouTube video and make sure every hardware is operating. And then you can try modifying the LabVIEW program to feedback control the stage using interferometer. And think about different ways of using all 3 sensors advantages for diagnostic and feedback purposes. And to tune the PID on top of what you're doing, Leizo will provide a tutorial in one of the following weeks that could be helpful for some teams. And to prepare the error budget, Stuart Smith from UNCC will provide a tutorial soon. So I created a Reddit forum so that whatever the questions you ask is visible to everyone, so each of us can learn from each other. But it doesn't stop you from emailing the committee. Yeah, make sure to ask for help. Yeah, we'll respond to you as soon as possible. So the deliverables for the preliminary presentations, this will be held on Zoom and it'll be strictly 4 minutes. And then followed by Q&A from the committee. We'll provide live feedback and each teams will be told what time they should show up on Zoom. So you'll be presenting your metrology and control efforts with nice images. So 3 main deliverables are, the first one, show the 10-second interferometer stability sampled at 100 Hertz without supplying any air to the air bearing stage. The next one is report feedback controlled step responses of these 4 different steps with 5-second dwell time sampled at 100 Hertz. You can use either interferometer or encoder for feedback controlling this. So if you choose to use interferometer, provide the reading of the line scale when you do the step response. If you choose the line scale for the feedback, report the interferometer reading. Then also provide the preliminary error budget. Before the conference in Boston, what she's going to be doing there, we will reveal it soon in a detailed manner. By November 5th, submit a 2-page report. Make sure to keep it a 2-page. This can include the challenges you overcame and the novel implementations, and it must include the error budget. And you can update the error budget on November 13th midnight, which is the challenge day. And you can do this after looking at the challenge environment at the conference. These are the key dates. The closest one is the preliminary presentation on the 20th. These are where you can find the resources of this year's Student Challenge. Thanks to the organizing committee, they show up every week on Friday, and without them, none of this is possible. And not only them, we also have people who don't participate in the meeting weekly, but they provide great support to make all this happen. Yeah, thank you.